Today on Quickly Quantum, can two rival quantum computing companies checking each other's homework finally give us a quantum advantage claim durable enough to believe? Before that, in the headlines, IonQ gets its hands on real 256 qubit chip samples on the road to 10,000 qubits. A $9 billion quantum campus on Chicago's South Side runs into an angry town hall. Nvidia doubles down on being quantum's classical backbone instead of building its own chip. A new paper proposes packing qubits into nanomechanical spins. And India opens a quantum chip foundry with its own 10,000 qubit ambitions. Welcome back to Quickly Quantum, your daily brief on the quantum frontier. It's Tuesday, August 18th, 2026. Let's get into it. Let's start with IonQ, because the roadmap talk just got a little more real. The company says it's now received actual chip samples for its 256 qubit system. Physical qubits sitting on a chip, not a promise on a slide, and it's moving into integrated system testing. The next milestone, 10,000 physical qubits on a single chip by 2027, with a second chip networked in to hit 20,000 qubits by 2028. Now, this traces back to IonQ's acquisition of Oxford Ionics. @NetCreate argued on X that if Oxford Ionics' EQC and WISE architectures scale as intended, 10,000 qubits doesn't appear to face a fundamental wiring or density barrier, with the bigger challenge shifting to interconnecting multiple chips rather than building one ever larger chip. And at Tech Innovations, a quantum investor on X walked back some of his own earlier skepticism, writing that his no lasers framing for Oxford Ionics was too clean, and that, quote, electronic qubit control is real and it is not marketing. An antenna is built into the silicon chip. Worth remembering, this is chip samples and a roadmap, not a shipped 10,000 qubit machine. Yet. Now, from chips to concrete, literally. As @Chicago Reader reported on X, quote, at a packed South Chicago town hall, residents demanded the mayor explain his support for the Quantum Shore development. That town hall, called Community Over Quantum, drew hundreds of Southside residents demanding Mayor Brandon Johnson kill the permits for the $9 billion quantum computing campus planned on the old U.S. Steel Southworks site. The project anchors big names, IBM, PsiQuantum, Inflection, and roughly $500 million in state funding. Residents, led by the group Southside Together, call it a rebranded data center and want the permits revoked, the tax rebates pulled, and the city's $5 million commitment withdrawn. Johnson didn't budge. He wouldn't disavow the project, but he leaned on his own data center moratorium, saying, quote, innovation cannot take place at the expense of environmental justice. According to Block Club Chicago, his departure drew boos and jeers from parts of the crowd. The project's CEO insists this is a research and microelectronics campus, not a data center, and site remediation will proceed regardless. Here's the pattern that matters. As quantum hardware needs more power and water to scale, this exact fight is likely to hit more cities than just Chicago. Nvidia is playing a different game entirely. According to reporting from EE Times, Nvidia isn't trying to build its own quantum processor at all. It's betting on being the classical compute backbone underneath every qubit type that ends up winning. Its CUDA-Q software, DGX quantum systems, and NVQ-Link already plug GPUs into error correction and control hardware for partners like QEra, Quantinuum, and PsiQuantum. That's the same playbook Nvidia ran in AI and robotics. Sell the shovels, don't dig the mine. And the timing lines up with a June 2026 executive order on quantum and fresh CHIPS Act funding for the sector. Federal support Nvidia can capture no matter which qubit architecture eventually wins. Now, here's the honest caveat. Nvidia's quantum-related revenue is reportedly still undetectable next to its roughly $194 billion data center business. So this isn't moving the stock. It's a long-term hedge, positioning Nvidia at the center of quantum computing's plumbing, regardless of who ends up owning the actual qubits. Quantum Zeitgeist reports on an early-stage idea worth flagging. Researchers are proposing a new kind of qubit built from nanomechanical resonators, tiny vibrating structures, combined with strain-sensitive solid-state spins, aiming to pack quantum information more densely than today's bulkier transmon chips. The reported numbers, a fidelity exceeding 0.98, preparing what are called cat states, a way of spreading a qubit's information across many photons for built-in error protection, and a fidelity of 0.95, reading that state out optically in a single shot. The pitch is density. Today's surface code error correction needs roughly the square of the code distance in physical qubits per logical qubit, and bosonic encoding like this could shrink that footprint substantially. Now, this is a single paper, and we haven't independently confirmed these numbers. They haven't been reproduced by outside groups yet, and the design doesn't grapple with actually fabricating and wiring many of these devices together. File it under promising, not proven. The Quantum Insider reports that India's sovereign quantum manufacturing push just got a serious anchor. QPIAI opened a quantum chip foundry in Bengaluru, an 8-inch fabrication facility already capable of producing superconducting processors with up to 128 qubits, with founder Nagendra Nagaraja setting a target of scaling to 10,000 physical qubits by 2027. The company says it's made a substantial investment in the facility so far, with more planned as it expands. QPIAI has already built 4 processors, including a 9-qubit fluxonium-based chip called UQT that it says shows promise for error-corrected logical qubits built from many noisy physical ones, wired together to actually protect the information they carry. Now, this fits a bigger pattern. Alongside China's grid trials and the billions the US has funneled through CHIPS Act awards, countries are racing to control their own quantum chip supply chains rather than depend on foundries elsewhere. But we haven't independently confirmed QPIAI's foundry capacity claims. This is one company's account of its own facility, and hitting a 10,000 qubit target on a roadmap says nothing yet about whether those qubits will actually work well together. Our main story today, call it the cross-check, whether one quantum computing company checking a rival's homework is enough to finally make a quantum advantage claim durable. Quantum advantage is the industry's holy grail, a real quantum computer solving a problem faster, or more accurately, than the best classical supercomputers can manage, on something people actually care about, not a contrived math puzzle. And the field has been burned on that claim before, with hero demonstrations later matched or beaten by cleverer classical algorithms. So the methodology behind today's story matters as much as the result itself. Back in late July, IBM published 3 quantum advantage papers, and it did something the field hasn't really tried before. It posted the underlying circuits on a public quantum advantage tracker months in advance, essentially daring classical simulation researchers to prove it wrong before IBM even claimed victory. One of those 3 papers, a collaboration between IBM, the error mitigation company Quantinuum Japan's RIKEN Institute, and BlueQubit, used Qedma's error mitigation software, which cleans up noisy quantum results without needing full error correction, running on IBM's Heron processor. The team modeled what's called a flow-K quantum magnet, a periodically driven magnetic system, essentially simulating how atomic spins interact when you pulse them with energy on a regular beat, scaled up to 74 qubits. At that scale, multiple state-of-the-art classical methods failed to agree with each other. One effort reportedly threw 500,000 CPU core hours at Japan's Fugaku supercomputer trying to replicate it classically, and still came up short of a consistent answer. Now, here's the part that actually got Quantinuum, IBM's competitor, talking. The research team didn't just publish and move on. They cross-validated key data points from that 74-qubit result on completely different hardware. Quantinuum's H2 trapped ion machine and its newer Helios system, using a totally different qubit technology than IBM's superconducting Heron chip. And they found matching results. So does that count as proof or just a really good coincidence? So how does this land practically? Let's stack up what people are actually saying about it. Quantinuum's own account was blunt about the significance, writing on X that this paper, quote, extends beyond the reach of the state-of-the-art classical methods considered, calling it evidence of a quantum advantage result, and crediting deadliest BlueQubit and its RIKEN collaborators. That's notable phrasing. Quantinuum is bragging about someone else's paper because that paper happened to validate itself on Quantinuum's own machines. The study's co-authors, writing separately on LinkedIn, framed the cross-platform agreement as proof the physics itself is real, not some quirk of IBM's Heron chip, its particular calibration, or Qedma's specific error mitigation recipe. If two totally different hardware platforms, IBM's superconducting qubits and Quantinuum's trapped ions, produce matching numbers on the same physics problem, that's a much harder result to wave away than a single vendor's self-reported milestone. But let's not skip past the skeptic's argument, because it's a fair one. Quantum advantage in this paper means something specific. Multiple state-of-the-art classical simulation methods failed to converge at 74 qubits within a finite compute budget, even after burning 500,000 CPU core hours on Fugaku. That's genuinely hard. But it's not a mathematical proof that no classical algorithm could ever crack this problem. It's evidence that the ones tried so far, with the compute available, couldn't keep up. Classical algorithms have surprised this field before, clawing back claimed advantages years after they were announced. And the community's own quantum advantage tracker, the same one IBM used to invite scrutiny here, still has other candidate claims sitting open and unresolved. So which is it? A durable result, or just a harder ceiling on classical simulation that a smarter algorithm eventually clears? Here's what actually shifts my thinking. Quantinuum isn't the one claiming the advantage here. It's the outside party doing the checking, on its own hardware, with numbers that could have just as easily embarrassed IBM if they hadn't matched. That's a real incentive structure working in favor of trust. A competitor had every reason to find daylight between the results, and didn't. We've also said before that IBM needs quantum to be the answer to its broader strategic bet, with whether the market actually buys that still an open question. A paper like this, cross-checked by a rival, is about the strongest single data point in IBM's favor since we started asking that question. Now, add to that the methodology IBM built around this, publishing circuits on a public tracker months before claiming victory, specifically to let classical simulation researchers take their best shot first, and you've got a genuinely different posture from the hero demonstration era. It's not proof positive, but it's the most rigorous packaging a quantum advantage claim has had in this field. And that's exactly the question hanging over the field right now. Critics of quantum advantage claims have pointed to a pattern of overinterpretation and slow, blocked replication in peer review. And this paper was built from day one to answer that critique before anyone had to raise it. That's a genuinely different posture than the industry's hero demonstration years, and it's why I'm not filing this away as just another vendor headline. Time for the hype check. 3 separate collaborators, a public tracker built specifically to invite refutation, and independent confirmation on a rival's completely different hardware. That's about as much rigor as a quantum advantage claim has ever shipped with, even though advantage here still means classical methods couldn't keep up with the compute thrown at them, not a mathematical guarantee that they never could. I'm calling this one a 7. Zoom out on this for a second. If cross-vendor validation like this becomes standard practice, who actually wins? IBM and contradictions get real credibility, Quantinuum gets a louder marketing story it didn't even have to write, and the skeptics warning about a replication crisis lose their cleanest counterexample, at least for one paper. If you're building a business on a quantum advantage claim nobody else has checked, this is the new bar you're being measured against. If today's episode helped you make sense of the quantum news, follow Quickly Quantum wherever you listen, and if you've got a minute, send it to someone who still thinks quantum computers are science fiction. This has been Quickly Quantum, an AI-voiced podcast created and built by a real human using today's cutting-edge technology. Nothing you heard on this show is financial advice. I'm Brian Lampert, and I'll catch you all tomorrow. Take care.